Hello, everybody. Hope that everything's okay with you today. We are here to present you a live broadcast brought to you by Victory Online Academy. My name is Alejandro, and I'm a physics faculty for Victory Online Academy. And today we will be introducing some ideas related to topic number 3 of the IGCSE physics syllabus. And we will be diving into one of its sections, which is section 3.2. And we will be discussing the reflection of waves as well as the refraction of waves. And we expect to broadcast for about half an hour. It will take a quick tour through the theoretical concepts related to this two-wave phenomena, and then we will be solving some problems. Okay, let's get started. First, I would like to introduce you to some of the keywords that we will be using throughout this topic. We have a diagram here, and I would like to guide you through the different elements that are being presented here. This vertical black line right in the middle of the screen represents some kind of a boundary. You can think of it as a mirror that separates the space in two parts. On the left side, we have the real part where light is allowed to travel. And on the right side, we have like the other side of the mirror, the side on which light cannot travel, the side on which waves are not allowed to enter. And whenever this situation occurs, whenever a wave reaches a boundary through which it cannot pass, a reflection is going to take place. And what we are here at the left top side of the screen is a blue point that will be representing an object. And this red line is representing one of the possible rays of light emerging from that object. It's obviously traveling in a straight path until it reaches the mirror, until it reaches the boundary. We have traced a green dotted line here, which is perpendicular to the mirror, that has no physical interpretation, but the geometrical line that is perpendicular to the boundary. Normally it is defined as a line that is perpendicular to the boundary, perpendicular to the mirror. The ray that's incident on the mirror will be reflected, and the law of reflection states that the angle of incidence, which is defined as the angle between the normal and the incident ray, will be the same as the angle of reflection, which is defined as the angle between the normal and the reflected ray down here. Now, for someone that's standing on the bottom left side of this diagram, a ray would be received as if it were coming from the other side of the mirror, from a point located on the other side, which is what you see every day when you watch yourself in front of a mirror. You receive light as if they were coming from a copy of you on the other side of the mirror. We call that the image of the object, and it is located at the same distance from the mirror as the object is. It is the same size as the object. We say it's a virtual image. That's a technical word that we use to say that there's no real light coming from the image. It's on the virtual side of the world. Now, for different positions of the object, of course, if I change the position of the object, of course, the position of the image will change, will follow the object. That is what you experience every day when you move in front of the mirror. And if we take a second to analyze how a different ray will be reflected, all I have to do is change the position of the normal. And if we take a closer look to this ray now, we can see that the rays reaching the mirror at this point down here will be reaching with a higher angle of incidence, and therefore it will have a higher angle of reflection. All the rays can be seen simultaneously in this diagram, and what we see is a collection of different rays. That's what is usually emerging from an object, rays in all possible directions, as rays of light are emerging from me in all possible directions, and that's why the camera that I have in front of me is capturing every point, every tiny dot of the wall behind me. And each one is being reflected with a different angle because each one is reaching the mirror with a different angle. And in each case, the angle of reflection is the same as the angle of incidence. So this is what the IGCSE syllabus asks the students to know. These are this is a copy from the syllabus of the IGCSE. And to summarize the idea behind the reflection of light, we will say that every mirror produces a reflection, okay? Rays from an object reflected of the mirror, rays from an object reflected of the mirror as if they were diverging from an object behind the mirror. That's it. That we call that the image of the object. The image is the same size as the object. The image is virtual. That means no rays actually pass through the image. It's just a geometrical projection of what we see from this side of the mirror. And the image is the same distance from the mirror as the object. Now, the speed of the wavelength, and its frequency remains unchanged, right? The wave is traveling through the same medium when going to the mirror and when being reflected from the mirror. And the medium is what defines the speed at which the wave will move, the speed at which the wave will travel, and it is unchanged. Same for the wavelength, the same for the frequency. And the law of reflection states that the angle of incidence is equal to the angle of reflection, and that the incident ray, the reflected ray, and the normal are always on the same plane. That's it. Now, let me take you now into a different phenomenon, the second phenomenon that we will be exploring today, which is called refraction, and it takes place when a wave is allowed to enter a different medium, when a wave is allowed to enter a different medium and it travels at a different speed. Waves tend to travel at different speeds when entering different mediums, and that's what we will be exploring right now. Now, this will be a slightly more complex diagram, so don't worry, we'll take it slowly. The diagram that is being shown in here represents a separation between two different mediums, shaded with this light blue color. We have a mirror that can be considered as water or some kind of glass or whatever. And on the upper side of the diagram, we have a medium through which the wave will be traveling at a higher speed. It can be considered as air, because that's the fact between water and air. Light travels at a slower speed through water than the speed at which it travels through air. And the same goes for the glass-air interface. So on the lower side of this diagram, we have a medium shaded in this light blue color, through which light is going to be traveled at a lower speed than on the upper side. We have the same dotted green line vertically kind of in the center of the diagram, which represents the normal, the separation between those two mediums. And I'll introduce an incident ray. Now this line then here will be representing a ray of light traveling through, let's say, water, and reaching at this point the interface between water and air, with an angle of incidence that at this point is kind of small. We have the value up here, 6.15 degrees. I can increase the angle of incidence, and by increasing the angle of incidence, of course, I will be changing the position of the incident ray. When reaching this water-air interface, part of the energy that the wave carries, it will be reflected, as we just described, following the same law that we have just described, the law of reflection, that states that the angle of reflection is the same as the angle of incidence. And part of the energy that the wave carries will be allowed to enter the other side. Now, this is where I need to take things down a bit in terms of speed, because I need to introduce these geometrical constructions that are represented what we call wavefronts. Now, these gray lines are representing points that are in phase with each other, and you might just take a second to realize that each gray line in here is perpendicular to the incident ray. And if I press play, you will see this gray wavefronts traveling towards the water-air interface. That is it's showing the direction in which the energy of the wave is being propagated. As each of these water wavefronts enters the other medium, it will suffer a change in speed. Now, in this example, we are assuming that in the upper side of the diagram, the waves will be traveling faster, and that will imply that the part of the wavefront that first reaches the boundary, it will move ahead, it will move forward, it will be advanced in terms of the rest of the wavefront. So this is showing what the changes of the wavefronts will be. You can see here that each of the wavefronts that have already entered the faster medium have moved forward, at least compared to the direction in which the wavefronts were traveling through the other medium. Now, each ray must be, which is a very important rule, must be perpendicular to the wavefronts at all points. Wavefronts are perpendicular to the rays. So on the other medium, the refracted ray must also be perpendicular to this wavefronts. So what we see here is that if we follow that rule, we must accept the fact that the wave will change the direction in which it's being propagated. And this is what we call reflection, which is the change in direction through which the wave is traveling when entering a different medium. You might have realized already, if not, I'll guide you through it, that the separation between wavefronts in the slower medium is not the same as the separation between wavefronts and the faster medium. The distance, that separation between consecutive wavefronts, is called wavelength. Wavelength, you might have heard that term before. And it changes when moving into a medium through which the speed is different. If the speed is different, the wavelength is higher, as you can probably see in this diagram. Through the faster medium, the wavelength will be bigger than through the slower medium. But not the frequency, right? The number of waves reaching each point in the boundary per second remains constant, right? Wavefronts are not being created or destroyed at the boundary. The same number of wavefronts are reaching the boundary in every second than the number of wavefronts that are, exit the boundary, going to the other side. So change in speed, change in wavelengths, but the frequency remains unchanged. Okay, let's go back to our theory now. So for the reflection of light, we have a definition. We'll say that it is a change in direction of a wave when traveling from one medium to another due to the change in speed. Okay. Speed and wavelengths are changed, but frequency stays the same. Okay, with this, frequency cannot change, and that is the definition of what refraction means. When a wave decreases its speed, it is refracted towards the normal, which was not the case in the diagram that we have just shown. When a wave increases its speed, it is refracted away from the normal. This is what we have just saw on the diagram. Now, let me take you back into the diagram one more time. We have then here the incident ray with an angle of incidence on here between the incident ray and the normal, and a refracted ray with a higher angle of refraction, higher than the angle of incidence. It's a consequence of entering a medium through which waves are traveling faster. And I would like to show you what the complete image will look like when all the rays are considered. We have the incident ray, the reflected ray, and the refracted ray. Now, if I change the angle of incidence as it is being increased, you can see that the refracted ray, the one on top in here, it's moving away from the normal as the incident ray is. But I am approaching, as I increase the angle of incidence, a position in which the refracted ray, it's almost getting perpendicular to the normal. Now, a very important process takes place at that point and beyond that point. When the refracted ray reaches that point in which it's traveling parallel to the surface, perpendicular to the normal, we have reached a very important angle, which is defined as the critical angle. That's the name that it's being given. It's just a name. Okay, don't worry. We will say that the critical angle is the angle at which the refracted ray travels parallel to the surface, perpendicular to the normal. But beyond the critical angle, light or waves cannot be refracted, and all the energy that is carried from the wave fronts that are incident to the boundary is being reflected. And no light is going to be refracted. There's one way that has escaped my diagram. Don't pay attention to that one on top. Never mind. Okay, so let me take you back to our notes. We'll say that there is an angle at which light is refracted parallel to the surface, perpendicular to the normal, and that angle is called the critical angle. The angle of incidence, if the angle of incidence is greater than the critical angle, there is no refracted ray, and there is a process called total internal reflection. If the angle of incidence is less than the critical angle, the incident ray will split into a refracted ray and a weaker reflected ray. Okay? Now, I have a small note up here that we kind of need to, well, you probably know it already, but it's something that the IGCSE wants you to remember. It's that when water travels from a deep region into a region in which the water gets shallower, the speed is decreased, and therefore the wavelengths are going to be decreased as well. And the opposite happens when water travels from shallow region into a deep region. Wavelength is going to be increased because speed increases. Okay, enough of that. Now let's see if we can put this into practice by solving some of the problems that were included in past papers from different years. Shall we? Okay, just give me a second. That's it. Now, what we are being asked here in this question that was included in the paper 2 of the extended version on February-March 2020, which was a few months from this video. Problem number 25 asks us the following: which diagram shows how light from a candle is reflected by a mirror and shows the position of the image formed? Different diagrams are being shown in here, and all we're being asked is to identify which one correctly describes what how light is reflected. Now, you can probably, likely, and hopefully use your intuition to probably even guess that if we have an object such as a candle placed in front of a mirror, the image of the candle has to be located on the other side of the mirror, placed perpendicularly at the same distance. So you would likely and probably be discarding option D, because the image of the candle is located somewhere else. And the same happens with option C. You see, the object is up here, the image, it cannot be on that place. Now, for options A and B, we have the image correctly placed, but for this one, for B, we have an angle of incidence which is not the same as the angle of reflection, sorry. Words are too similar. The angle of incidence is not the same as the angle of reflection, so we will be discarding B and we'll keep A as the correct option. Okay, next one. Now, hopefully you will identify the diagram by just taking a quick look at it as a diagram in which wavefronts are being shown, and as well as rays represented by these two arrows. And here we have a region 1 and region 2, deep water, shallow water. Now, by just looking at the diagram, we can identify that we have a higher distance between wavefronts in region 1, this distance, which is called the wavelength, and it's represented by a Greek letter. You might have seen this letter before. It's lambda, that's the name of the letter. It's used to represent wavelengths. And the wavelength in region 1 is not the same as the wavelength in region 2. It's different wavelengths. It's much shorter in region 2, and that implies that we have a higher speed in region 1 than in region 2. The speed is being changed because, well, this problem is about refraction, and refraction is about the change in speed of a wave. So let's read the problem. It goes like this. I'm sorry. This was included in the October-November 2019 session. It's paper 1 from the core syllabus, problem number 21. Now, most of the problems that we will be solving today, you will find them at the 20-something part of the multiple choice, because the IGCSE presents the problems and exploring the syllabus in always the same order, so it's not a coincidence. Most of the problems of the multiple choice paper that are related to waves are to be found in the 20-something, 21, 22, 23, always the same order. Okay, let me read the problem. I'm too distracted. The diagram shows wavefronts on the surface of water viewed from above. The question is, which row is correct for the wavefronts moving from region 1 to region 2? Now, the name of the process is, of course, refraction. We haven't explored what diffraction is throughout this video, so right now it's kind of easy to guess that it's not going to be diffraction, which is a different process that will probably be explored on a different video. And between these two options that are correctly describing the name of the process, we are asked to identify if the speeds of the wavefronts in region 1 are different or the same. Of course, they are different because that's what refraction is about. That is what refraction is about. So we'll keep with option C as the correct one. Okay, let's jump into a different problem now. Problem number 24, once again, the 20-somethings, October, November 2019, paper 1. Question goes like this. Total internal reflection may occur when light reaches an air glass boundary. Now, I'll stop here to clarify something. I've said a few minutes ago, something that you might already know, but just in case, light travels faster through air than through glass. And that implies that total internal reflection can only take place when traveling from glass into air. It can only take place, as in the diagram that I've shown recently, when light travels from a slower medium into a faster medium. Cannot take place on the other direction. It only takes place in one direction, from the slower medium to a faster medium. And in this case, from glass into air. There's no total internal reflection from air into glass. Light is always allowed to enter the glass, but it's trapped inside the glass if the angle of incidence is too high. That's the main principle through which optical fibers operate. Light is being trapped inside the fiber. So let's answer this problem. Under which conditions is light totally internally reflected? Sorry. So the first column, medium in which light travels towards the boundary. Medium in which light travels towards the boundary. It must be traveling in glass, towards air, but it's traveling in glass. So we'll be discarding options A and B because this is not correct. And what about the angle of incidence? Well, for total internal reflection to occur, this is what we want. We want total internal reflection to occur. We need to have an angle that's greater than the critical angle. We need to have an angle that's greater than the critical angle. So we'll keep option C as being the correct one. Okay, next problem. 23 now, May, June 2016, goes like this. The diagram shows a ray of light in air incident on a glass block. Now we have light traveling from air into glass, okay? Some of the light is refracted down here, and some of the light is reflected up here. Two angles P and Q are marked on the diagram, okay? Which row gives the angle of incidence and shows whether the ray undergoes total internal reflection? Okay, the angle of incidence. Well, it is defined as the angle between the incident ray and the normal. So in this case, it's Q. P down here is just a complementary angle. Geometrically, that's how it's called, complementary angle, but it's not the angle of incidence, has no special name. So Q is the one we were looking for, and we must state whether it undergoes total internal reflection. Well, of course not. It cannot happen. Traveling from air into glass, total internal reflection cannot occur. And also, we are clearly being shown that refraction is taking place. We have a refracted ray, so it was not totally internal reflected. So we'll keep with option C, right? The angle of incidence Q, total internal reflection. No, that's it. Okay, last multiple choice problem. And hopefully identify some wavefronts in each of these diagrams. Problem 22 of the February-March 2020 session. Please, if at any point you have doubts about something that I described, something I explained, or something was unclear for you, please let me know in the comments below, and I'll try to answer all the comments at the end of the video. Goes like this. Waves on the surface of water travel from deep water to shallow water. Which diagram shows the correct path of the waves in the shallow water? Well, to begin with, let's identify that diagram C is showing two rays traveling on the same side of the normal. If we trace, if we trace the normal perpendicular to the boundary, we have two rays that are on the same side of the normal. We can hopefully identify that this cannot happen. For option B, same thing is being shown. If we trace normal line perpendicular to the boundary, we can probably and hopefully identify that the incident ray reaching the boundary, represented in red color here, is on the same side of the normal, and that cannot take place. Refracted waves will always be on the outside of the normal, so we will be discarding this option. Now, the only difference between diagram A and diagram D can be identified as that this diagram shows a shorter wavelength than the one it had before. And for diagram D, we have higher wavelength. And the same happens with the speed, higher speed, refracted away from the normal. Well, it's all about identifying what is a change that takes place when water waves travel from deep water into shallow water. And the only possible way to solve this problem is to know that when entering shallow water, the speed of the wave is reduced. That's why problem is solved by identifying A as the correct option. Once again, please let me know in the comments below if you have doubts, if there is something that needs to be clarified further. Okay, that was it. Please feel free to visit. Let me take you to visit our website, www.victoryonlineacademy.com. You can follow us on Facebook and Instagram. And of course, thanks for watching. Thanks for